All right, what's good, everybody? These are going to be my editorial or my solution explanations for educational code forces round 110. Now, I did not do this contest officially, but I did read through the problems. I did do the contest, but not on my main account. And pretty much, I know how to do A through E, so those are the problems that I'll be going over today. I won't be going over problem F, presumably, because it's pretty difficult. And if you're watching this video, you probably would be like okay without getting problem F, you know? So yeah, let's just get right into it. So problem A is, okay, this one is just pretty much implementation. I don't think I really have to go over it. Pretty much, you're given 4 numbers. All you have to do is to just do what the problem statement says. I don't know what else there is to say. If you don't know, I feel like everyone solved problem A because it literally told you what to do. So yeah. Problem B. Okay, so problem B. So basically how this works is that I'll write the important condition over here. So if we assume that I and J is, or I guess to be more specific, if I is strictly less than J, then we want to count how many pairs exist such that the GCD of A at I and 2 times A at J is strictly greater than 1. And we want to count how many pairs, how we can maximize the number of these pairs that exist. So one thing to notice is that GCD is it's essentially a commutative function. So what I mean by that is like if we have the GCD of A and B is always equal to the GCD of B and A, right? So in other words, if a problem was to simply just count how many pairs of like GCD of AI and AJ existed, then we could literally just print any permutation of the initial input, and that would be a correct answer. Because the number of pairs that exist don't change. All they can do is they can get rearranged. But in this case, we have like this condition of multiplying by 2. So we know that the only time we can increase the number of pairs is if there's ever a case in which one of these numbers is odd and one of these numbers is even. So to write this out, if, for example, AI is odd and AJ, or actually, well, not AI and AJ, but rather just like A and B, where A and B are like some values in the array. So if A is odd and B is even, the GCD of A and 2 times B, it could be greater than 1. For example, if both A and B are multiple of 3, but it's also possible that their GCD is equal to 1. However, if we were to rearrange it like this, where we have GCD of like B and then 2 times A, notice that B is even and A is also even because now we're multiplying it by 2. And because we multiply it by 2, and both of these numbers are even, we know that the GCD in here has to be at least 2, which in turn is strictly greater than 1. So what this implies is that we want to put all even numbers before all odd numbers in order to maximize our answer. And that's the only thing that we have to worry about. Because all other pairs of GCDs, if they don't need this factor of 2 to have a GCD greater than 1, it doesn't matter how you rearrange it, their GCD will always stay greater than 1. So what implementation will look like is that you take all of these numbers, you put all the even numbers first, so E is an even number. So you put all even numbers first as some prefix of your construction, and then you put all the odd numbers on the suffix. So this is an odd number, odd number, odd number, and so on. And so after you get this array like this, you simply just run an n-squared like naive checker to count how many pairs have a GCD, have like this GCD strictly greater than 1. And so this runs in n-squared time, and because n is less than or equal to 2000, this is okay. So yeah, that's how problem B works. I'll go to problem C now. Problem C. Okay, so there's actually multiple solutions that exist for this problem. I'll go over the solution I did, which is basically which I think is actually pretty easy to implement and easy to understand as well. So pretty much, let's try to think of this problem as some sort of a DP. So it's logical to think that if we have some substring and we want to append an extra character to a substring. So for example, if we have a valid substring like 10101 blah 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 whatever, and we want to append some character at the end of the substring to create another substring, the only thing that we care about from the substring is what the last character is over here. And the only two possibilities it can be are 0 and 1. So in order to create a new string from this previously existing valid unstable string, all we have to do is to know what this last character was. And so, for example, if this last character was 0, then this would have to be a 1. And if this last character was a 1, then this would have to be a 0. And that's just how, and that's pretty much where the DP comes from. So if we define DP at I, and then at I and last, this is equal to the number of unstable strings ending at index I with the last character, character equal to 0 or 1, because this parameter over here is either 0 or 1. And so the way this DP works is that the base case is obviously DP at I and 0, it's equal to 1 if it's possible for the first character to be a 0. So in other words, if the first character is equal to either a 0 or a question mark. So this is 0 or question mark. And then also DP at, DP at 0, 0. Because I'll assume this is a 0 index DP. And if it's at 0 and 1, this is equal to 1 if the first character is 1 or a question mark. And so the way that the recurrence works is that it depends on what the ith character of the input string is. So if the ith character is equal to, more specifically, if it doesn't equal to 1, then that means that this string at the ith character, ending at the ith character, can have, it can end with a 0. So in other words, DP at I in 0 is going to be equal to 1 plus the DP of the previous string, how many strings that ended at the previous index that ended with a character of 1. Because we want to make sure that our digits are always alternating, which is why we can only append the 0 to a pre-existing substring that ended in a 1. And it's a similar case for if the ith character if it doesn't equal to 0, which means that it's possible for that ith character to be a 1. And so then it would look something like DP at I and 1 is equal to 1 plus DP I minus 1 and 0. And then the final answer is simply just, and so yeah, this is what the DP recurrence looks like. And the final answer would look something like this. Let me just erase this. So the final answer is essentially the sum, so for I equals 0 up to n minus 1, assuming this is 0 indexed, of course, it's the maximum of DP at I and 0 and DP at I at 1. And the reason being is that we want to count all beautiful substrings. So we first iterate over this I, which is essentially the right boundary. And then we also want, and then from this ith substring, we know that if it's possible for an ith substring to like be over here, we want to essentially consider which choice of the ith character will maximize our leftmost boundary. And that's why we take a maximum of these two, and we sum them over all I. So yeah, that's problem C. We have problem D and E left. Okay, so problem D, if you know how segment tree works, this problem is very easy. It's pretty much just exactly how a segment tree works. So pretty much, the way you can visualize this is, let's assume we have like 8 players at first. So in other words, we have 7 games that we care about. So if we imagine our 8 players as like this bottom layer over here, 1, 2, 3, 4, 5, 6, 7, 8. Then we have one game that happens here, one game that happens here, one game that happens here, and one game that happens here. And you can draw them like a tree like this. And so after like the first round of games happen, we have 4 winners left among these 8 total contestants. And then we just continue like these rounds of games. So the winner of like these 2 games then face each other off in here, and then the winner of these 2 games face each other off in here. And then finally we have 2 contenders left, and then that's decided by one final game up here. So this is pretty much exactly what a segment tree looks like. If you were to imagine all of these nodes, all of the like bottom nodes as having a value of 1, then the combine operation depends on I guess what do you call it? The instruction that the input gives. So for example, for the first game, if it's a character of 0, then it only considers the possible winning people from its left child. If its character is 1, then it only considers the possible winners from its right child. And if the character for that game is a question mark, then it can consider both its left and right child. So what that looks like in segment tree terms is, for each node, it depends on how, it's essentially like a combine function that's different for every node. So in this case, for example, if this was a 0, then it would only take a left child, so it would be a value of 1. For this, if it's only the right child, then it only considers here, so it's a value of 1. But if this game over here was a question mark, then it's essentially a sum of a left and a right child, which is 2. So yeah, I don't know if there's much else to say about this. It's pretty much just like, understand how segment tree works, and it's pretty straightforward. You just need to realize that when you modify how one game is like performed, you only need to change the values of at most 18 other nodes in this tree. And the reason being is, like, say for example we wanted to like modify this node over here, then we would need to modify its parent, and then we need to modify the parent of its parent, and so on, all the way to the root. And because the depth of this tree is at most k, and k is less than or equal to 18, doing 18 operations for every query is totally fine. So yeah, if you don't know how segment tree works, I recommend going on YouTube and looking a tutorial up. I think Second Thread probably has a segment tree tutorial, and I remember watching his and he explained it really well. You can also just go on like cpalgorithms.com and just Google segment tree and like look at how the implementation works. There's a lot of free resources that are just really good for learning data structures like this in general. So yeah, that's problem D. Moving on, problem E. Okay, so problem E was, okay, so the strange thing about problem E is that these queries are forced to be online, because the problem would be a lot easier if you didn't have to worry about, if you could process the entire tree and then answer all these queries like out of order offline. But you're not allowed to do that. So there's actually multiple ways to approach this problem. I know some people used a splay tree, which I'm not going to go into because one, I'm not really sure how it works, and two, I think it's definitely overcomplicating the problem. And you don't even need to know what splay tree is in order to solve this problem. All you need to know is what binary lifting is. So I'll just write it up here. Binary lifting. If you don't know what binary lifting is, I would recommend just like going online to look it up. I think CP Algorithms is an amazing website, and I feel like not enough people talk about it. So, and it's also completely free. So I'll definitely put that website in the description if you want to go check it out. It gives like so much information about a lot of things, and I think it's great. So yeah, the easy way to explain this is to think of it like this. Let's assume our tree currently looks like this. I'll just like draw a random tree. It doesn't really matter what it looks like. It just has to be a tree. And we want to answer a query on this tree. Say, for example, at this node over here. So this is a query node. The first thing to notice is that it gives a really important condition that the cost of gold of a child will be strictly greater than the cost of gold for any of its parents. So for example, if the cost of gold at this node was A, and the cost of gold for this node is B and C, we know that A is strictly less than B, which in turn is strictly less than C. And that's what makes this problem possible to solve. So with this like observation, you can notice that we always want to consider taking nodes, or like, because we want to consider all like gold bricks that are on the path from the root to this current node. We always want to start taking gold from our root, because that's guaranteed to be the cheapest place to take gold from. So you start over here, and then you can essentially think of a process like this. We start on this node over here, and we keep on taking gold until either we have enough gold, or if this node runs out of gold. So after we process this node, if we still need more gold, we go from A and we move on to B, and then we process the gold in here. And then if we still need more gold after taking all the gold from A and B, we move on to C, and so on. And if we simulate this process and we get all the way to the same node and we still don't have enough gold, well then we just stop our process here, because as defined in the problem statement, if we don't have enough gold, we just buy as much as we can and just print the cost of that. So what makes it so important that the fact that these cost values are strictly increasing? Well, the reason why it's strictly increasing is so important is that allows us to maintain some information as we add a node to a tree. So for each node, we want to maintain like a few things. We want to know for each node, what is the total number of like gold bricks, of gold tons, I guess, from root to the node. So from root to V. So this is the first thing that we want to keep track of. And then the second, and then like, that's probably the most important thing, right? Yeah, that's the most important thing. And then also, obviously for these nodes V, we also want to store the actual cost and like how much gold they have in general, which is already given to us in input, because that's just given as AI and CI. So the way that we can maintain this information is that we can simply, when we add a new node to this parent, we already know what this parent value for the total number of gold tons from the root to this parent node is. And so the value for this new node is simply just this previous value plus AI. So yeah, that's pretty straightforward. And so this is like one type of information that we want to keep track of. And so the other like sort of information that we need to keep track of is we also need to keep track of their lowest common ancestors. And this is where binary lifting comes in. because because when we add a new node to this tree, we know what its direct parent is. So that's just equal to, like, if we have parent at node v, and at 0, this is going to be equal to p at i. P at I. And this 0 means it's like what is like the 2 to the power, what is the 2 to the power of 0 ancestor? And so essentially, like, what is the direct ancestor above it, because 2 to the power of 0 is 1. And then we just use a standard binary lifting table where we have like the parent of v and like 2 to the power of b, where b is strictly greater than 0. This is just equal to the parent of what is this a parent of? So we first go 2 to the power of b minus 1 steps up, v and then b minus 1, and then from this node we go b minus 1 more steps up. So I'm not going to go too much into how binary lifting works. Again, if you don't know how it works, then check out the links in the description, and those are like some really good resources in which you could learn this trick from. So now that we have our binary lifting table, this basically means we can essentially binary search on this path from this current node to the root. Now, I say binary search in quotation marks because it's not exactly it's not quite the binary search that you might be thinking of, or the one that you might be used to. It's binary search that's implied through binary lifting. I think if you know binary lifting, you know what I'm talking about. But if you don't know what I'm talking about, then essentially you can think of it as if v is a number, or not v, that's a bad variable name, I guess k. If k is the number of like ancestor jumps that is needed, then we can represent k in its binary form. And because our binary lifting table stores all parents for all nodes that are like some power of 2 above it, we can compute k in log n time, because k has at most log n bits in its base 2 representation. So yeah, and so what this means is that we use binary lifting as like a binary search to figure out where is the highest node that we can take that's an ancestor of this query node, in that the path from the root to that node that we care about has at least wi tons of gold. And so once we find that, once we find like the highest chain that has at least this many tons of gold, we can simply just take the sum of all of these nodes, and then for that last node we take like some of the gold tons in that node. And so in the end, this means that, and we can solve that particular step in O of 1 time, which means that this is this method in total should look something like this. It's an online algorithm, and this means, and I believe, if I'm looking at this correctly, every time we add a node, so adding a node, this is I believe it's log n time. And the reason why this is log n time is because we need to update our binary lifting table. And so then, and as for each query, we need to use our binary lifting table to figure out the best answer that we can choose. So this is also log n time. So this essentially reduces into q times log n time, which should run in time. So yeah, that's problem E. And that's pretty much it for this video. If you have any questions, feel free to put them down in the comments. I'll definitely try to answer them to the best of my ability. So yeah, if you enjoyed this video, then like and subscribe. I don't know what else to say. Yeah, See you guys for Codeforces round 724, which, by the way, if you don't know, round 724 is going to be a very special round, and you'll find out why very soon.